Hello, my name is Rebecca Matasovsky. I'm an associate editor at ASHRAE Journal. Thank you for joining us for today's webinar, part of the ASHRAE Journal Supplier Webinar Series. The series provides information to ASHRAE Journal readers and to others about products and technology of interest to industry professionals. ASHRAE does not review supplier webinar presentations. The following presentation has been prepared by Train. The subject is Design Considerations for Commercial VRF Systems. Today's speaker is Cy Zamangir. He is the VRF System Specialist for Train in San Diego, California. He is responsible for selection and design assistance for all VRF equipment sales in his local market. He began his career in 2016 and quickly became an expert in VRF system design for high-performance commercial buildings. He is also involved as the co-chair of his local intergenerational employee resource group at Train Technologies. It focuses on providing an environment where employees from all generations can provide insight and alternative perspectives. He graduated from San Diego State University with a Bachelor of Science degree in Mechanical Engineering. He currently resides in San Diego with his wife, Kelly, where they enjoy biking to the beach. Ty, the microphone is all yours.
Good afternoon, everyone on the East Coast, and good morning to everyone on the West. Welcome to today's webinar on design considerations for commercial VRF systems. Like Rebecca said, my name is Cy. I'm the VRF Specialist for Train in San Diego. Now that we have introductions out of the way, let's go ahead and get started. Variable refrigerant flow systems are often used to electrify heating, provide a scalable HVAC system design, and intelligently transfer heat from one part of a building to another. On today's webinar, I'll be providing an overview of the different system types and designs of variable refrigerant flow systems. Then, I will discuss different humidity control strategies and the ventilation equipment used to achieve the desired results. We will then wrap up with a discussion on different system control methods. Have you ever noticed how in the HVAC industry, we often name air systems based on the zone control equipment used and assume that it's adequate to describe it? Variable air volume system, fan coil systems, water source heat pump system, chilled beams. While this is a way to create a picture in our head, we don't really know if the picture and assumptions that you have are the same as what I have, and it can lead to confusion or misunderstanding. There's just so much to define about a system, including how it's controlled, to really understand the system and how it will perform. The same is true for variable refrigerant flow systems. They come in many forms. So let's take a deeper look at the scope of what we mean when we say VRF system. There are typically three major subsystems that complete a VRF system, but there could be more. First, there's the VRF equipment and refrigerant piping. Here we are showing an air source VRF system. It is made up of the outdoor units. If the manufacturer uses a modular design, there will be more than one. The branch controller and the zone terminal units, often referred to as indoor units. And finally, the interconnected refrigerant piping. This VRF system recirculates air from the room and provides temperature control in the zones. VRF systems are known for using variable speed compressors and fans, but they have several unique characteristics beyond their variable speed nature. First, VRF systems have one outdoor unit connected to many indoor units. This gives VRF systems their zoning capability. Second, they are reversible heat pumps. This enables electrified high CLP heating. And third, they can offer simultaneous heating and cooling capabilities. This means some zones can be in heating while others are cooled at the very same time. It does this by recovering heat within the system. The second subsystem is the ventilation system, which could be a dedicated outdoor air system, or DOAS for short. It is made up of 100% outdoor air unit that conditions and ventilates air before delivering it to the zones. There are numerous ways to address the outdoor air treatment, and I will discuss them more in detail. The ventilation system includes ductwork and the outdoor air room diffusers to deliver the ventilation air to the zones. This DOAS also provides demand control ventilation with the addition of pressure-independent variable air room diffusers. The final subsystem is the controls. Each piece of refrigeration equipment has its own factory-provided unit controller. The VRF equipment operation is coordinated by interconnecting their unit controllers on a proprietary network. The outdoor unit controller directs the VRF system operation. The ventilation system has its own unit controller and typically operates only during occupied hours. Control coordination between the VRF and ventilation system can be handled a variety of ways, from standalone operation to a building automated control system. The focus of this program is to discuss each of these subsystems and their various options. Now for a quick poll to gauge everyone's familiarity with VRF. On average, how many commercial VRF system projects do you design each year? I'll give everybody a moment to answer. Excellent. Let's see our results. So we see a majority of everyone is dealing with around 0 to 5 systems per year. That's not bad. Awesome. Now that we've done a quick overview of VRF systems, we'll go into the 4 design considerations in more detail. As mentioned earlier, there are many elements that comprise a complete VRF system. This VRF system wheel is intended to bring focus to each portion. Right now, I'm going to focus on the system types and common VRF equipment. Here, we have a simple matrix that represents the basic VRF system options. The heating and cooling unit can be either air source or water source. They are often also referred to as condensing units. While air source units are located outdoors, water source units are located inside the building. The system can be a heat pump or, as you see below, a heat recovery system. This is where the level of zone control flexibility is determined. Let's take a closer look at the system options. VRF heat pump systems are a heating and cooling changeover system. This means they can only operate in one mode or the other. When in heating mode, all zones have heating available to them. No zones can cool. When in cooling mode, all zones have the cooling available to them. No zones can heat. So, it has a heating mode and a cooling mode. Of course, the transition between modes is not instantaneous. During those transitions, the system neither heats nor cools. So when it comes to heat pump systems, there are several changeover algorithms available as part of a heat pump VRF system control network. From a practical standpoint, no changeover algorithm is without its potential comfort compromise. Examples of algorithms used for changeover methods include using a schedule, polling zones, establishing a decider zone, or using outdoor air temperature. This leads designers to limit heat pump systems to cooling-only applications or applications with a common demand for heating or cooling in all zones. Examples for this might be a call center with a large open office area, a library interior, or even a school area like a cafeteria. Some of these types of spaces could be served by a large central station air handling unit using a linear expansion valve kit or LEV kit applied with a VRF condenser unit. We'll go into more of those applications a little bit later. For those wishing to use heat pump systems, even given their comfort risk, careful system zoning design is critical to minimize comfort complaints. It probably makes more sense to break up a building into multiple systems to increase building control flexibility. In this example, we show a small building zoning the west exposure separate from the east exposure. An hour-by-hour load analysis will help the system designer to determine if this will work effectively. Of course, if selecting a heat pump system requires the designer to select multiple systems, the cost savings of the heat pump option may be negatively impacted. Now, a VRF heat recovery system can provide heating in some zones while simultaneously providing cooling in others. All this done on a common refrigerant system. The VRF system uses heat recovery as a technique for providing this capability, thus the name. Heat recovery systems require a unique outdoor unit. Some manufacturers' heat pump outdoor units do not readily convert into the field to heat recovery outdoor units, and they require a piece of equipment referred to as a branch controller for 2-pipe systems and a heat recovery control unit for 3-pipe systems. A manufacturer's difference for heat recovery is often referred to as 2-pipe or 3-pipe systems. This describes the number of refrigerant pipes and phases of refrigerant being sent between the outdoor unit and the branch controller or heat recovery control unit. I will discuss this difference in a little more detail shortly. All systems do have 2 pipes between the branch controller or heat recovery control unit and the zone terminal units. Finally, all VRF systems require the use of the manufacturer's provided system design software for pipe sizing and other system requirements. Zoning with heat recovery systems is straightforward, with some exceptions, because the loss of comfort control is mitigated with the simultaneous heating and cooling capability. When the system is in a simultaneous operating mode, some of the zones can be heating and returning liquid, while others use liquid for cooling. The outdoor unit is providing either net heating or net cooling capacity, depending on the individual zone loads. Using heat recovery may enable fewer systems to be used on a building and actually save first cost, all while improving comfort. VRF systems, regardless of the type, offer a variety of zone terminal units. Many of them are ductless and mount on the wall or ceiling. There are also ducted versions available as well, mainly for those applications demanding the HVAC equipment be less visible or deliver improved zone air distribution. There's also the option to use linear expansion valve kits, or LEV kits. These refrigerant modulating devices can be useful to incorporate advanced air handler unit options, as well as benefiting from long line runs for split air handler units. These LEV kit air handler unit combinations can be used to serve spaces such as large auditoriums, large open office spaces, or to add a dedicated outside air system to the VRF system. There are other options which we did not cover in their entirety, but do deserve to be mentioned. There's the option to provide water-cooled VRF for spaces with already existing water treatment facilities. This can also incorporate the use of ground-coupled water source systems used to efficiently cool VRF systems. Also, one of the most important design considerations to account for is the refrigerant concentration limit of a space. ASHRAE 15 specification says that a space served by a refrigerant-based air conditioning system must not exceed the specified refrigerant concentration limit for each specific refrigerant. The system refrigerant concentration limit can be determined by calculating the volume of the smallest space to be served by the VRF system and coordinating the design to never exceed the RCL for that space. Also, when designing a VRF system, it is important to determine whether the capacity of your system should exceed the 100% indoor to outdoor ratio. When a system has more indoor unit capacity connected to it than provided by the outdoor unit, we say that the system has a diversity ratio. Exceeding a system's diversity ratio means that if all zones call for heating or full cooling, then each zone's total capacity will be derated by the amount of diversity on the system. So, it is important that when designing a VRF system, that your demand for capacity be distributed throughout the zones served by the VRF system. Great detail must also be considered when determining the installation location of your VRF system. When systems in high humidity environments run in a defrost mode, large amounts of condensate will occur, which can lead to pooling if drainage is not properly accounted for. That's why proper condensate routing methods should be considered when installing outdoor VRF condensing units. When selecting between 2-pipe or 3-pipe heat recovery, you must take into consideration what type of building you are serving and how the specific VRF system can serve either your high-rise or low-rise zoning application. Please consult your preferred VRF manufacturer for more details about how their VRF system applies to your specific needs. And lastly, cold climate operations can be tricky with VRF systems. Some manufacturers have condensing units which can provide heating down or below 0 degrees Fahrenheit or -17 Celsius. Also, low ambient accessories can be provided to offset the low temperature applications as seen in many parts of the country. And now for another quick poll. What would you consider to be the roadblock preventing you from designing more VRF systems? Would it be the lack of product knowledge, lack of design opportunities, lack of available equipment, or are you just simply new to HVAC? We'll take a few seconds and let's go ahead and check out the results. Awesome, so we have a lot of folks here that are new to HVAC, so hopefully this VRF presentation is beneficial to everybody. Excellent. So now on to humidity control. At what temperature should the air be delivered? 55 degrees, colder, warmer? How much outdoor air should be supplied to each zone? ASHRAE standard 62.1, the ventilation standard, is often used to compute the design for outdoor air requirements for each zone. Also, the corresponding outdoor air intake rate for the equipment or system that supplies ventilation. How exactly does outdoor air affect the humidity design of your commercial space, and how can this be addressed with a complete VRF system design? As you see here, there are 4 main considerations when determining how humidity should be addressed. The first being, how should the ventilation system be configured for humidity-related concerns? Next, how do we determine the supply path for the ventilation system? Then, at what temperature should the outside air be provided to the space? And finally, what role does the dew point design play when introducing outside air into the space? When it comes to outside air delivery into a space, there are 3 main methods: delivering unconditioned air, sometimes via a booster fan, to a zone terminal unit. There's delivering passively conditioned air with the use of an energy recovery ventilator, and delivering actively conditioned air via a DOAS or makeup air unit. Depending on your outside air requirements, the total system design, one of these three methods will suit your ventilation requirements. Then, the next important step is to determine your ventilation supply path. The two main methods for doing so are either the direct-to-terminal method or direct-to-space method. Some of the advantages of the direct-to-terminal method are that this method helps to ensure that the required outdoor airflow reaches each zone. This method also avoids the cost and space it takes to install additional ductwork as well as diffusers. And this method also has the ability to provide an even outside air distribution through VRF terminal units. Some disadvantages of this system are that the VRF terminal units must operate continuously to provide the outside air, and that the measurement and balancing can be a bit more difficult during the commissioning of the system. There's also the direct-to-space configuration. One of the advantages of the direct-to-space method is that this method helps to ensure that the required outdoor airflow reaches each zone. As a byproduct of this method, VRF terminal fan coil units do not need to be operating in order to distribute air. This method also allows the dedicated outside air system to operate during unoccupied periods. This method also provides the opportunity to downsize VRF terminals if colder conditioned outside air is to be used. Conversely, the disadvantage of this method of delivery is mainly due to the additional ductwork and diffusers needed for first costs. Next, a big part of determining the level of humidity control is whether to deliver colder conditioned air to space or whether to deliver neutral conditioned air to the space. Designers have the liberty to make a lot of dehumidification related decisions. They might choose to supply conditioned ventilation air at a predetermined supply air dew point, like 55 degrees. Or they may choose to compute the proper supply air temperature based upon the zone latent loads and the desired zone humidity level. Using the neutral supply method for delivering outside air to the space provides better control over the zones where loads are different from one another. Also, in places where it's applicable, electric reheat for humidification control may not be allowed. Providing a cold supply air temperature to a space allows for less capacity needed by the zone terminal units, which in turn requires less CFM from the zone terminal unit, therefore reducing the overall energy needed for cooling. There also needs to be some consideration when it comes to this method of outside air delivery. Overcooling can become an issue if not mitigated properly, and some steps may be needed to make sure that this does not happen. In order to avoid this, the following steps can be taken. Apply supply air temperature return, use demand control ventilation, and apply heat to offset the overcooling in a space using the VRF terminal unit. Simply choosing a specific temperature, such as 55 degrees, seems to fit a rule of thumb, but it doesn't address the actual latent loads. To ensure space humidity control, an analysis to determine the appropriate supply air temperature would be needed. And that analysis would need to account for the design's space latent loads, as well as the design dehumidification weather. Lastly, dew point design should be a big consideration when delivering outside air into a space. These specific methods do include passive cooling with the use of an energy recovery ventilator, neutral cooling, which uses the 55-degree rule of thumb to supply conditioned outside air to a space, and the low dew point method, which in high humidity environments may be required in order to meet strict relative humidity set points or comfort cooling. Depending on your design environment, addressing humidity concerns does not have to be difficult. For example, right now we're analyzing whether or not the neutral method of air delivery should be used in this particular case. But we start off with an outside air condition of 93 degrees wet bulb, 93 degrees dry bulb, 80 degrees wet bulb, pretty moisture-laden air. Indoors, we have a space temperature of 73 degrees and a 73 degrees dry bulb and a relative humidity of 50%. Let's ask ourselves, will the 55-degree rule of thumb apply for this scenario? Well, let's take a look. As we cool down to 55, we see we cool down to a dew point temperature that is slightly higher than the dew point temperature already in the zone. When introducing the 55-degree temperature air into the space, the indoor air temp does decrease, although we're adding more moisture into the space than already present. So in this case, the neutral air delivery design would not be the desired method of providing outside air into the space. A proper HVAC system must take into consideration the design of the dedicated outdoor air system unit, as well as the zone terminal systems, in order to ensure that proper space temp and humidity is being addressed. With a proper control solution and an adequately sized ventilation system, your comfort cooling system will have the ability to turn even the most humid environment into a pleasing space for all tenants. Also, when selecting your VRF terminal units, make sure that they are properly sized based on the appropriate ASHRAE conditions. This is important in order to get the capacity that you need, based on the terminal unit's nominal tonnage. Designing at a temperature much higher or lower than the equipment's rated conditions may result in the D-rate of the equipment's published cooling or heating capacity. Let's take a look at what that means. As we earlier discussed diversity factor, this is important to consider when determining how your system design will function, particularly when you have zones with similar cooling profiles. Depending on a zone's exposure, an improperly sized and designed VRF system can have a negative effect on the total capacity of each terminal zone unit. If your selection does not consider the full demand capacity for the zones that experience similar temperature profiles during peak demand, D-rated factors will cause zones to be undercooled. Designers should also consider that outdoor air loads may not vary too much throughout the day, so caution should be taken when applying diversity factors to a VRF system, especially if you're using an LEV kit with a DOAS air handler unit connected to the comfort cooling system. And at this time, we'll go ahead and take another second for another quick poll. When designing for indoor air quality, what type of system would you use for this application? Would it be a dedicated outdoor air system? Would you use the terminal zone units or a makeup air unit? Or all of the above? Another second, and let's check our results. Excellent. So a lot of you chose to use the DOAS system as your main point of indoor air quality. And there are also other applications that involve the terminal zone units and the makeup air unit. Excellent. Now let's move on to the topic of ventilation. When it comes to ventilation options available to VRF systems, there are a variety of methods available to supply either conditioned or unconditioned air to the space, as we previously saw. In this section, I will discuss the various options available to designers when considering the appropriate method. Energy recovery ventilators are an inexpensive method for providing either direct-to-space or direct-to-terminal zone unit method of providing conditioned air, outside air. An energy recovery ventilator uses an air-to-air heat exchanger to precondition the outside air by exchanging heat and sometimes moisture with the exhaust air stream. There are no cooling or heating coils used to precisely condition the ventilation air to an exact temperature or dew point. So, in most climates, there will be times during the cooling season when the unit supplies conditioned ventilation air hotter and or wetter than the space set point. And there will be times during the heating season when the unit supplies air colder than the space heating set point temperature. Conversely, a dedicated outdoor air system uses a cooling and heating coil to condition the outside air to a specified set of conditions. This allows the ventilation air to be adequately dehumidified without relying upon the VRF terminal units to offset some of the ventilation load. The dedicated outdoor air systems are often standalone, air-cooled DX units, or a package unit. Or some might be split systems featuring a VRF coil connected to a VRF system with a linear expansion device, as we saw in earlier slides. So it is important that it's important to note that equipment conditioning the outdoor air also affects space humidity. An ERV provides passive cooling and dehumidification, while a dedicated outdoor air system provides active conditioning. Said another way, the ERV does what it can, but is constrained by the ambient conditions and air-to-air energy recovery device, while the dedicated outdoor air system actively conditions to a specific defined set point using cooling and heating coils. As we discussed, ventilation systems play an important role in providing conditioned and unconditioned outside air to a space. But most importantly, ventilation systems can also provide indoor air quality solutions, which in today's world has become an important consideration for owners and tenants. We see here what we consider to be the 4 key pillars of indoor air quality, aligned with the CDC guidelines for operating HVAC systems: dilution, exhaustion, containment, and cleaning. A comprehensive VRF system design based around indoor air quality will have addressed each of these 4 core ideals. Dilution is used to increase the amount of fresh air in order to make sure that the stale air is less likely to be recirculated into a space. By disabling demand control ventilation, the air supply will remain consistent throughout the day, instead of relying on the level of occupants in a space to determine the outside air requirements. It is also recommended that when a building is unoccupied at either the beginning or at the end of the day, that the system purge be done by ramping up the outside air supply to remove any remaining particles that may be lingering in the air. Exhausting a space is critical to making sure that the contaminated air is removed from the occupied building. One critical space that should always have some sort of exhaust method during occupied times are bathrooms. It's also recommended that exhaust systems should also be operating during times of pre- and post-occupancy purges, like during the dilution stages. Containment is a strategy used in order to maintain humidity levels in the desired range. This is done to make sure that airborne pathogens are less likely to reproduce. This strategy is made possible by the use of humidity sensors controlled by a sophisticated building management system, of which we will discuss in more detail shortly. Lastly, ensuring that the air in a system is properly cleaned is perhaps the most important pillar of indoor air quality. by ensuring that a system has adequate MERV-rated filters for occupied spaces, as well as other methods of airborne contaminant reduction, such as UV lighting, the occupants of a space can rest assured knowing that the building's HVAC system is not only providing comfort cooling, but is also addressing indoor air quality concerns. As always, please be sure to size and design any method of filtration in conjunction with the equipment static pressure restrictions. This is important also when sizing for VRF terminal zone units. It should be said that the design of a VRF system up until this point will have all relied on one key aspect to ensure their maximum efficiency. This is the controls. We will now move on to the discussion. Of the final section of our VRF design wheel. Now that we have an understanding of VRF systems and the importance of both the terminal system and the ventilation systems and how they play a role in humidity control, let's discuss how VRF systems are enabled and operated. VRF system designs have the capability to operate with a variety of control options. One of those control options is to independently control both the VRF and DOAS equipment separately. An independent control system will often be simple to design and install. It should also result in the lowest cost approach to control a VRF building solution. But that simplicity will come with some disadvantages. These include 2 control panels for the 2 different systems, possibly from 2 different vendors, little to no coordination between the systems, and a lack of advanced building control options. Scheduling strategies like supplier temperature reset, morning warm-up, and others might not be as easily available with independent control. When it comes to integrating controls, providing connectivity can be useful. Improved connectivity can enable useful additions like dashboards, alarms, remote connectivity, and the ability to control multiple buildings. An integrated system can also control other building functions such as lighting. With an integrated control system, there is a single system controller for the building. This single controller approach can yield a number of advantages. First, integrated systems control. An integrated systems control greatly improves the ease of a building's operations. With a single system controller, a single access point is used for this system coordination. This access point can include some valuable user enhancements like a simple user interface and standard graphics. With integrated building level controls, advanced control schemes will be more readily available. These control schemes include demand control ventilation for energy savings, morning warm-up or morning dry-out for energy and comfort, and a supply air temperature reset at the outdoor unit. Also, your preferred control supplier will also likely present you with the option for a more advanced control option. Some control suppliers can offer the benefit of remote site monitoring as an additional service on top of the high-level control solution for your total VRF system. Some of the benefits of this additional offering include having the ability to diagnose a system even before a technician visits the site. This allows for fewer site visits, which can save costs associated with all those technical visits. If a service contract is provided, alarms and trending data can be also provided to determine periods of higher usage and even predict problems before they can become a potential system disruption. For more information regarding additional control offerings, I urge you to reach out to your preferred VRF manufacturer to recommend the appropriate control solutions for your building needs. Excellent. So today we've talked about a number of important VRF topics and how high-level VRF system design can be broken down into a few high-level considerations to ensure a successful system. A few of the key takeaways to consider when determining what kind of VRF system will suit your needs are the system type, which will heat recovery be required, or will a heat pump suffice? For humidity control, can we just get by on monitoring and controlling outdoor air, or will we have to control the specific space humidity? We talked about the ventilation system. We asked, will a VRV be sufficient, or will the building require a dedicated outdoor air system with mechanical cooling? And lastly, we discussed the system control, and we asked ourselves, will independent control be sufficient, or will integrated control be needed? And lastly, your preferred VRF system supplier is going to be your best resource when it comes to making the selection that is just right for you. My advice is to reach out and request that you take a design course for their proprietary VRF selection software. Thank you everyone for joining today's webinar, and now we'll move on to the question and answer portion, in which I urge you to ask any questions that you'd like related to the design of VRF systems for commercial spaces.
Great, thank you, Sai. Hey everyone, I'm Sophia Krieger. I'm the Ductless and VRF Solutions Marketing Manager at Trane, and I'm going to be helping Sai out with the Q&A today. As he mentioned, please use the questions panel to submit any questions you have if you haven't already done so, and we will do our best to get through as many as possible today. Okay, so Sai, the first question is, let's say I want to add equipment to the system later on. Can I do that without impacting the rest of my design?
That is a great question. So VRF systems, most VRF system manufacturers have the ability to let you operate systems with only 50% of the outdoor unit's capacity. A big benefit of doing this is that, let's say a different space of your building is getting zoned out later on. You can come back to your VRF branch circuit controller if you're using heat recovery, and add on to the additional ports on your branch controller. I highly recommend also using isolation refrigerant ball valves, especially for when you have to take a unit down for some unseen error, or for adding additional terminal zone units to your system later on.
Great, thanks. Another question is, what are some common mistakes you see made when designing a VRF system?
So some of the common mistakes are that systems are, I've seen systems that are somewhat undersized and that space loads aren't quite accounted for. Also, some designers may not use the appropriate temperature setting tools on the VRF system selection software. So I highly encourage that a course be taken on the specific VRF system selection softwares. And each manufacturer is going to have their own selection software to choose from.
Awesome. Okay, so the next question is, if you have an AHU with 2 DX coils, 1 heat and 1 cold, can these be connected to a VRF with heat recovery?
Yeah, that is definitely possible. So using the air handler, the LEV kits for air handler unit operation, those different air handler units can be used with the branch controller of the VRF heat recovery unit to either do heating or cooling simultaneously or separately.
Awesome. Okay, the next question is the branch controller typically located outside next to the HR unit or inside?
I highly recommend that the branch controllers be placed indoors. The reason being that some branch controllers, if not all, are not rated for outside applications. I have seen in some instances where manufacturers can fabricate outside what we kind of refer to as like dog houses for the branch controllers. Even though there aren't any moving parts, heat will be given off from these units. So it is important that some sort of DC fan be used to provide cooling for those units. But if there is space inside a building, I highly recommend that that be your first method of installation.
Great. Another branch controller question came in. The question is, do your branch controllers require a condensate drain and or insulation at the branch controller?
So for the Mitsubishi product line, the branch controllers will need a condensate line for the system, being that our branch controllers are not foam filled in the factory from the factory, to ensure that there is the ability for field servicing and the heat exchanger inside the branch controller has the ability to be easily changed out.
Thank you. Another question is, what is the maximum length of piping between outdoor and indoor units, or how many max floors can be served with outdoor units mounted on the roof?
So that's a great question. Some manufacturers are limited based on their application. Also, depending on the type of units that you're using, you might get some line length applications where they are restricted based on the size of the terminal zone units. For example, well, without any elevation changes, the Mitsubishi systems can go up to 197 feet for horizontal from the branch controller. But when you apply a larger 6-ton ducted unit, then just because of the line size requirements, there is a slight restriction to those distances. And, you know, all VRF manufacturers do have their limitations. So it is very important to take a more in-depth design course for your preferred VRF manufacturer.
All right, great, thank you. Another question is, are there any problems with noise from the control box and heat recovery systems? Yeah,
so an appropriately sized and designed VRF system should have a minimal result of any noise being generated by the heat recovery unit. Also, I do not recommend putting these boxes in spaces that are occupied in which low-level noise is required. So my first point of advice when placing the branch controllers, and that goes for all different manufacturers, is to find some sort of service closet, either a mechanical room or in a hallway where, like I said, the low noise level is going to be a factor.
Thank you. Next question. There are a lot of questions. I love this. The next one is, are there any VRF systems on the market today that will allow for introducing untreated outside air via the indoor unit?
So I see this application all the time. Depending on your geographic location, I'm over here in San Diego, California, just miles away from the beach. So in applications, certain distance from saltwater sources, salt air sources, I would highly recommend that some sort of coil treatment be done to the terminal zone unit. But with the application of a booster fan, there are contact points that are provided by your specific VRF manufacturer that will allow you to enable those booster fans to provide outside air to a space. But depending on your terminal zone unit, you are limited to a specific amount of outside air. So I would have to say consult your VRF manufacturer, your preferred VRF manufacturer, for those limitations.
Great. I like that sly brag of how close you are to the beach over there in San Diego. I don't have that luxury in Chicago.
Oh, yeah, I don't mean to humble brag, but.
All right, the next question is, what is the maximum cooling capacity size that VRF systems can handle?
The maximum cooling VRF. So there's a number of ways to answer this question. Right now, some VRF manufacturers have condensing units well over 32, 34 tons. As for terminal zone units, I've seen the top end of the terminal zone units at 8 tons, although if more tonnage is needed, we do have the use of the LEV kits, the linear expansion valve kits, which can be combined together with a large air handler unit to use as a terminal zone unit. So basically creating your own VRF system with the air handler unit of your choice.
All right, great. All right, ready for the next one? It is, can you add additional terminal units from a different manufacturer for future remodeling projects?
So every manufacturer's control schematics is going to be different. You know, LG has their VNet, Mitsubishi has their MNet, Carrier Daikin, they all have their own proprietary network. So it's like speaking a different language. If I were to get dropped into a Far East country, I probably wouldn't be able to speak that language. So I would have to say that using terminal zone units on a different manufacturer's VRF system is not going to be compatible, nor will the units might power on, but they won't communicate back with the outdoor unit. So I would have to say that that's not a smart decision to make.
Great. The next question is, how many indoor units can one branch controller typically handle?
So each VRF manufacturer has different sized branch controllers. One thing that I like is that some manufacturers' branch controller can handle more than one VRF terminal zone unit on one branch. The caveat of this is that all the units on that one branch will operate in the same mode. So you can have a heat recovery system, but if you have multiple units on one branch port, they're going to be limited to a heat pump application, which means all the units on that port are going to be either heating or cooling. Right now, Mitsubishi has the largest 16-port branch controllers, and each one of those ports can handle up to 54,000 BTUs per port.
Thank you. Somebody asked, the the refrigerant line lengths vary depending on whether the outdoor unit is above or below the indoor units, correct?
That is correct. So depending on whether you're placing the outdoor unit above or below the branch circuit controller, you will be limited to the line length limits per each VRF manufacturer. And this is mostly due to the amount of work that's able to be done by the VRF compressors.
Great, thanks. We have I think we have time for a couple more. The next one is, what is the best way to estimate the amount of refrigerant charge needed for a VRF system, including the charge for pipes inside?
So this question, I always come back to the VRF manufacturer's system selection software. There is old methods of being able to just determine additional refrigerant using pipe sizes and lengths. Although with the complex systems that we are seeing today, it's much more accurate method by entering in those lengths and pipe sizes. Pipe sizes are already going to be in the system, but entering in those lengths and the number of hard 90 elbows into your system. When talking to VRF system installers, I always recommend the use of long radius bends to reduce the amount of additional refrigerant in the system.
Thanks, Sai. All right, the next question is, can VRF system proprietary controls communicate via BACnet to base building DDC? We always have integration challenges.
So this is a good question. So typically out of the box, and when I mean out of the box is right from the factory with standalone controls, there really isn't going to be a method to communicate the controls via BACnet. In order to provide BACnet controls, your VRF system manufacturer will need to give you either a BACnet access license or provide a central controller that does have BACnet enabled on it. This same idea works with LawnWorks and other language protocols, other communication protocols. But I would always refer back to your VRF manufacturer for those specific requirements where you do need DDC controls. I know some applications, they don't want to run through BACnet and they want those hardwired control options. So always discuss with your VRF manufacturer what available control solutions that they have.
Thank you. Okay, we're almost at time, but I think we have time for one more, Sai. There are quite a few questions coming in, which we appreciate everyone's engagement, and we will do our best to follow up as necessary. But the last question is, what is the minimum ground source water temperature for a water-cooled heat pump VRF system?
That is a great question. Depending on your application and sizing, depending on where you're geographically located, that's always going to have to be referred back to the engineer's calculations. So I can't quite recommend the appropriate ground level water temperature, but that is a great question, which we can always provide more information a little bit later on.
Great, thank you. All right, so I think with that, we're gonna call it for time. But again, thank you everybody for your participation today. When you do close out, you'll have the option to take a quick survey. If you could take a minute to complete that, your feedback is always greatly appreciated. And so with that, on behalf of us at Train and ASHRAE, thank you for joining us today. Have a good rest of your day.
Thank you, everyone.